A 9-kilometer rock is heading straight for Earth. Scientists know exactly when it hits. And the world's response? Absolutely nothing. I'm FactSpark. If this kind of stuff blows your mind, subscribe because we're just getting started. So let's get into it. That's the setup of Netflix's Don't Look Up. And honestly, it's one of the most uncomfortably realistic disaster scenarios ever put on screen. But forget the movie for a second. The real question is, if a giant space rock were actually coming for us right now, what the hell would we actually do about it? Because here's the thing, we thought about it a lot, and the answers are equal parts brilliant and terrifying. First, how realistic is this scenario? Pretty realistic, actually. Objects called NEOs, near-Earth objects, are constantly being tracked. The really massive ones, the ones measuring several kilometers across, are few and well cataloged. But a comet arriving from the far outer edges of our solar system, one that nobody saw coming, that's entirely plausible. In 2013, astronomers discovered a comet roughly 500 meters wide that had a small but real probability of colliding with Mars within 2 years. And here's where it gets genuinely unsettling. The NEOs we should be most worried about aren't even the giants. It's the medium-sized ones, the ones we haven't fully mapped yet. Objects just tens of meters across, like the Chelyabinsk meteor in Russia, can go from a dramatic light show to entire cities flattened, depending on where they land. Scale that up to hundreds of meters, and you're talking about regional or even continental devastation.
So, before we go any further, I want to ask you something, and I mean it genuinely. If you found out a comet was 6 months away from hitting Earth, what would you do first? Drop your honest answer in the comments. No wrong answers here. Now, how do we stop one? The answer most people instinctively reach for is blow it up. Nuclear bomb, big explosion, problem solved. And honestly, that's almost always the wrong move. Here's why. The moment you shatter a massive space rock into fragments, you've traded one predictable problem for dozens of unpredictable ones. You don't know how the rock is structured internally. Is it solid, porous, a loose pile of gravel held together by its own gravity? You can't know for sure. And depending on that structure, your nuclear detonation might split it into 2 giant chunks or 1,000 smaller ones, all still aimed at Earth. You've just turned one bullet into a shotgun blast. So the serious approach, the one scientists actually talk about, isn't destruction. It's a nudge. Think about it this way. A collision between an asteroid and Earth is an almost impossibly precise coincidence of trajectories. 2 objects in the vastness of space arriving at the exact same point at the exact same moment. If you shift the asteroid's velocity by even a tiny fraction, we're talking centimeters per second, that small change compounds over months and years of travel into a completely different path. The rock sails right past us. That's deflection. And it only takes a push of a few Earth radii to make all the difference. The asteroid Apophis, for example, will pass Earth in 2029 at about 1/10 the distance between Earth and the Moon. That's close, but still a miss because the geometry worked out. Barely.
So what are the actual methods on the table? The most obvious one? Strap a rocket to it. Send a spacecraft, drill it into the surface of the asteroid, and use the engine to gradually steer the rock off course. Sounds straightforward. The problem is fuel. Rocket fuel is absurdly heavy, and getting enough of it to an asteroid is an engineering nightmare. That's where a wilder idea comes in: the electromagnetic catapult. Instead of bringing fuel, you bring a machine, one that drills into the asteroid itself, extracts material from its surface, and then flings that material out into space using powerful electromagnetic fields. The expelled mass acts like exhaust from a rocket engine, pushing the asteroid in the opposite direction. It's essentially turning the asteroid into its own engine. Both of these methods share a major weakness, though. You need to know the terrain. If the surface is too soft, too hard, too irregular, the mission could fail before it even begins. What if we didn't have to land at all? This is where the Yarkovsky effect comes in, and it's one of the most elegant ideas in planetary defense.
Here's the physics. Sunlight hits an asteroid's surface, heats it up, and that heat eventually radiates back out into space as infrared energy. That radiation, as tiny as it sounds, actually exerts a force on the asteroid. Over years and decades, it can meaningfully shift in orbit. So what if we amplified it artificially? Option 1, mirrors. A spacecraft deploys a large reflective surface near the asteroid and focuses concentrated sunlight onto a specific point. The intensified heating causes surface material to vaporize and escape, generating thrust.
The problem is that the escaping material, fine dust and gas, tends to coat the mirrors, reducing their effectiveness over time. Option 2, lasers. Mounted on a spacecraft, or even fired from Earth, high-powered laser beams could do the same job more precisely and without the dust problem. Option 3, and this one is my personal favorite, paint. Coating the surface of an asteroid with a highly absorbent material changes how much sunlight it soaks up, which changes how the Yarkovsky effect acts on it. Scientists have actually identified Teflon, yes, the same stuff on your frying pans, as a candidate material for this. We could theoretically save the planet by painting a space rock with non-stick coating. Wrap your head around that. Then there's the gravity tractor. The concept is almost zen in its simplicity. You don't touch the asteroid at all. You park a massive spacecraft close to it, not on it, just nearby, and let gravity do the work. The spacecraft's mass exerts a tiny gravitational pull on the asteroid, and over a long period, that pull slowly bends the trajectory. The challenge is station keeping the spacecraft in exactly the right position for months or years without being pulled down onto the asteroid itself. It requires constant precision thrusting, and that means fuel, which brings us back to the same old problem. There's also a concept developed in Spain, and it deserves way more attention than it gets, called the ion beam shepherd. A spacecraft equipped with 2 ion beam emitters positions itself near the asteroid. One beam fires toward the asteroid to push it, while the second beam fires in the opposite direction to keep the spacecraft itself stable. Clean, contactless, and remarkably elegant.
But here's the honest truth about all of these methods. They work, under the right conditions, which means the right size of asteroid, the right composition, and crucially, enough time. We're talking months to years of continuous operation just to produce a deflection of a few kilometers. If a massive object appears with only 6 months of warning, as in the movie, most of these techniques become completely useless. So what's the most practical solution we actually have? The kinetic impactor. You build a spacecraft, accelerate it to an enormous speed, and ram it directly into the asteroid. No explosion, just raw momentum transfer. Think of it like a billiard shot in space. This isn't theoretical anymore. NASA's DART mission, the Double Asteroid Redirection Test, deliberately crashed a spacecraft into a small asteroid called Dimorphos. And it worked. The impact measurably changed the asteroid's orbit. For the first time in human history, we intentionally moved a celestial body. That's not a small thing. But even kinetic impactors have limits. Against something truly massive, 9 kilometers, like in Don't Look Up, no amount of kinetic energy from a single spacecraft would be enough to shift the trajectory in time. Which brings us to the option nobody wants to talk about, but everyone knows is on the table. Nuclear deflection. Not explosion, deflection. The distinction matters. You don't detonate a nuclear warhead inside the asteroid. You detonate it close to the surface, in open space. The intense burst of X-rays and energy vaporizes the top layer of the asteroid's surface instantly, and the recoil from that vaporization, like an extremely powerful version of the Yarkovsky effect, pushes the rock off course.
Done correctly, the asteroid stays in one piece and changes direction. Done incorrectly, well, we're back to the shotgun problem. The precision required is extraordinary, but for a true extinction-level object, it may be the only option that generates enough force fast enough to matter. Here's where we stand today. All of these techniques are in early stages. We have the theories, we're beginning the tests, and DART was a landmark proof of concept.
but we're still a long way from having a reliable, ready-to-deploy planetary defense system. It's a bit like knowing the theory of firefighting, but never having built a fire hose. The gap between we understand how to do this and we could actually do this in an emergency is still enormous. And that gap is exactly what keeps planetary defense scientists up at night. The good news is that we're taking it seriously. Space agencies around the world have dedicated planetary defense programs. Telescopes are being built specifically to find undiscovered NEOs before they find us. And missions like DART are proving that deflection isn't just a sci-fi concept, it's real engineering. The bad news is that the universe doesn't wait for us to be ready. If something were heading toward Earth right now, our best bet would depend entirely on how much warning time we had. 5 years? Multiple options. 10 years? We'd probably be fine. 6 months? We'd better hope the nuclear option works, and works perfectly on the first try. So the next time someone tells you asteroid defense is a problem for future generations, remember this. The dinosaurs didn't have a space program. We do. The question isn't whether we can build the tools to protect this planet. The question is whether we'll build them before we need them.
Because in space, there are no second chances. If this kind of deep dive is your thing, you know what to do. Subscribe to Fact Spark, and I'll see you in the next one.